Section 4.3, how derivatives affect the shape of a graph. And so we're going to pick back up with what we were talking about in section 4.1, where we had started talking about the derivative, finding those turning points, using the derivative to locate our extreme values, right? Those local maxes and local mins, that kind of thing. But we're going to continue bringing back up discussion we've had about what the derivative tells us about the shape of a graph from our earlier discussions. Because remember, all of this started with the slope of the tan line, and then ultimately we use that to give us the quote unquote slope of the curve, whether the function was increasing or decreasing based upon whether the derivative was positive or negative, right? So we're going to kind of use that in conjunction with what we were talking about in section 4.1 to locate those maximum and minimum values of our function. And then we're also going to bring the second derivative into it as well and see what that tells me about the shape of a graph. So this section ultimately, again, I think tends to go pretty well because it does focus on discussions really that we've already had. There's really nothing new here in terms of especially the first derivative. Now, the second derivative is going to give us a little bit more information, but again, the process is very straightforward. So this also tends to go pretty well, but as I keep saying, you're going to be working with multiple functions here, so you've got to keep them straight. So am I working with the function itself? Am I working with f prime? Am I working with f double prime? Because we're going to be evaluating each of those to give us different information about the graph of our function or the behavior of our function. Right? So you've got to be organized, got to be neat, got to keep them straight, make sure I'm actually plugging values into the correct function. Okay? Otherwise, I think this goes pretty straightforward. All right, so increasing and decreasing. So like we said, this goes back really to what we've already said. If f prime is positive on an interval, then our function is increasing on that interval. All right? That's nothing new. Right? That's back from early on. And then if our derivative is negative on an interval, then we know that our function is decreasing on that interval. So we have an increasing function if our derivative is positive, and it's decreasing if our derivative is negative, right? So for example, let's let f of x, get this to work, let's let f of x be the function x cubed minus 3x squared plus 5. Let's find the intervals where f is increasing and decreasing, right? So it's all about the derivative, and increasing and decreasing function values. Now, if we're going to find where our function is increasing and decreasing, where do you think we're going to start? Well, like we talked about back in section 4.1, let's start by first finding where the derivative is 0, right? And then once we have those points or those values, those critical numbers we called them, then we can set our x-axis up into subintervals. And then this is something we did back, we were doing some applications previously with like velocity and acceleration. Remember, we were trying to determine where a function was speeding up or slowing down and moving forward and backward and that kind of thing. And we used those little test strips because we were finding where the derivative was 0. That was where our object or our particle was at rest. And then we checked to see where the derivative was positive or negative in each of those subintervals to tell us where the particle was either speeding up or slowing down, or moving forward or backward, or that kind of thing. So we use little test strips. That's what we're going to utilize here. And again, I just think it's easy to organize it that way. I mean, you don't necessarily have to do it this way, but you do have to make account of where your derivative is 0. I will find those critical numbers. Use those to split our function into subintervals, and then we're going to check the value of our derivative in each of those subintervals to see where the function is the derivative is positive or negative, where the function is increasing or decreasing. Okay? So, but again, be organized because at some point we're going to bring the second derivative into this as well. All right, so we want to know where our function is increasing or decreasing. So let's start with our derivative. Find your critical numbers. All right, so here's f prime. Power rule, nice little polynomial function. Go ahead and find our critical numbers. Remember, we set the derivative equal to 0. Solve that equation. I've factored it in this case, and I get x equals 0 and x equals 2. Okay. And so these are the locations or values of x where the derivative is 0. So notice I went ahead and labeled this as f prime. Make sure you're labeling your test strips because, like I said again, at some point we're going to have the second derivative as well. And then we just take a sample point from each of our subintervals. Remember, you can pick any number to the left of 0. I just plugged in -1. Now again, make sure you're plugging that into the first derivative because that's what we're checking, the sign of f prime. So if you plug -1 into f prime, now back when we did this before, I gave you a couple of different ways you could do that. You could either plug it into this, or you could plug it into this factored form if you find it easier to do it that way. So you can always plug it back into the original f prime, the 3x squared minus 6x, get your value. Or I can plug -1 into each of our factors. If you plug -1 there, that's a negative. You plug -1 here, that's also negative. Negative times negative is positive, right? And so I get a positive value for f prime. However you care to do it, but ultimately it's all about plugging those numbers into your derivative to determine the sign of the derivative, whether it's positive or negative. I don't care about the number itself. So you plug -1 in, you're going to get +9 actually, so that's a positive value. So that tells me then that that function is increasing on that interval from -infinity to 0 because our first derivative there is positive. Then we pick a number between 0 and 2. The most convenient one there obviously is 1. So I went ahead and plugged 1 into f prime, and you end up with a value of 5, or -5 rather, which is a negative value. And since our first derivative is negative there, then we know over this interval from 0 to 2, our function would be decreasing because our derivative is negative. And then we take a sample point on the interval from 2 to infinity, so I just plugged in 3. And again, you can pick any value you wish in the interval. Doesn't matter. The value of the derivative will always be the same for every value in the interval. So if you plug 3 in, you will get 9, or ultimately, like I said, it's a positive first derivative. So over that interval, our function would be increasing, right? So again, really, there's nothing new there. I mean, that's what we did back when we were talking about velocity and acceleration and position functions and particle motion and all of that. So we find our critical numbers, use that to set up our little test strip, and then we plug in sample points from each subinterval to determine where the derivative is positive or negative. And then where the derivative is positive means that our function is increasing. So we said we're increasing on the interval from -infinity to 0 and also on the interval from 2 to infinity. That's where the derivative was positive. And then we would say that f is decreasing on the interval from 0 to 2 because that's where our derivative is negative. Okay? Now, put this in conjunction with what we were talking about in section 1 with the local maxes and mins. Where do local maximum and minimum values of this function occur? And if you think about, again, the shape of this curve, and I'm just doing a general sketch of this graph just based on what this derivative is telling me. So we have the points where x equals 0 and x equals 2. We know that those are where the derivative is 0. Now what's happening on the left side of 0? We know the function is increasing, so the function is doing something like this. Then at 0, we know the derivative is 0, so the tan line is horizontal there, and then it switches from positive to a negative derivative, which means now on the other side of 0, we're decreasing, right? And then you're decreasing until you get to 2, where again we run into a 0 derivative, which means our tan line there again is horizontal. And then notice at 2 we have a change in our derivative from negative to positive, which means we're changing from decreasing to increasing. And so what we're looking for is at those critical numbers, do you have a change in the behavior of your function? And if you're changing from increasing to decreasing, then at that point you're going to have a local max. If your function changes from decreasing to increasing, then at that point you're going to have a local min. So again, it's a pretty straightforward observation. It's just based on what we already know about the behavior of the function, what the derivative tells us, increasing and decreasing. But it all starts with the critical numbers, because like we said, you're going to have a change in sign. It has to occur on either side of those critical numbers. So you start by finding where the derivative is 0. You check the sign of your derivative on each of those little subintervals to determine where the function is increasing or decreasing. And then if you have a change in that behavior from increasing to decreasing or from decreasing to increasing, then you're going to have a local extrema, whether it's a local max or min, depending on which behavior is taking place. Okay? So again, I think it's a pretty straightforward observation. Nothing tricky there. We call this the first derivative test. Okay? So we'll say, suppose that c is a critical number of a continuous function f. There's that good old continuity again we always have in these definitions. If f prime changes from positive to negative at c, right, then that means our function is changing from increasing to decreasing. Then that means at c we have a local max. And vice versa. If f changes from negative to positive at c, right, so if we change from decreasing to increasing, then at c we're going to have a local min. Now, it could be possible that f prime does not change sign, right? Maybe we have a case where our function is increasing, so the derivative is positive, and then when we hit our c value, the derivative there is 0, but then on the other side it's also positive. We've seen that like with the graph of like x cubed or something like that I think we had looked at before, to where we showed that there was a derivative that was equal to 0, but there was no turning point, there was no relative max or min, right? So of course then if f prime does not change sign at c, then there is no local extreme value there. There is no local max or local min at that point. Right? So we start by finding the critical numbers, and then we check to see what the derivative is doing on either side of that to determine the local extrema. Here's another example. Let's let f of x equal x squared times e to the x. So again, let's go through the same process. Let's find the intervals where f is increasing or decreasing and identify any local extrema. So we start with our derivative, find your critical numbers. So I got f prime of x, there's our product rule. And again, all the differentiation, that just goes back to what you know about differentiating functions. So this is a product, x squared times e to the x, so f prime of x, first d second plus second d first. And then I just went ahead and wrote this in factored form because we are going to set it equal to 0 to solve the equation. So I have e to the x as a common factor. I also factored out the common factor of x. That leaves you with x here plus 2 there, right? So there's f prime of x in factored form. We set it equal to 0 to find those critical numbers. Now, it's already in factored form. That has to be done to solve the equation. And then we set each factor equal to 0. Now, be careful of this factor, e to the x. Remember, e is a constant. It's approximately 2.72. You can raise it to whatever power you want. I don't care what x is. That's always going to be a positive number because it's a positive number raised to a power. So don't forget that. I see that happen. So, we just get thrown off because of the e thing. But e to the x is a positive number always. Right? So it's never equal to 0. So I don't care about that as a factor. But we do have the other factors of x and x plus 2. So I do get x equals 0 and I do get x equals negative 2. So those would be our critical numbers. So that's what I use to set up my test strip. And again, I labeled that as f prime because, again, we're going to bring the second derivative in. I want to make sure everything is labeled clearly. We don't confuse ourselves as far as what function we're talking about or what information we're getting from it. So then again, I just plugged in some sample points. So in the interval, something to the left of negative 2, plug something in from this interval. I went ahead and plugged in negative 3. So I got f prime of negative 3, which ultimately ends up giving me a positive value. Right? And again, remember, this is always positive, so I don't even care about that. All I care about is what's happening with this factor, and this factor. All right. But like I said, it's all in the comfort level that you have. If you just prefer to go ahead and plug that into the whole function, plug it into the whole function. All I have to determine is ultimately whether the derivative is positive or negative when you plug -3 in. And it ends up being a positive value. So then we took a value between -2 and 0. So the most convenient one there would be -1. And if you plug -1 into f prime, in this case, you will get a negative value. And then we take a value in that last interval to the right of 0, the interval from 0 to infinity. So I just picked 1. And you plug 1 into f prime, and again, here you do get a positive value. Now, don't fall into the trap of thinking these are always going to alternate. I have an example coming up where they don't. Okay? So don't presume that they will necessarily alternate positive, negative, positive, negative. May it be it happens quite often, but doesn't necessarily have to be that way. But then once we have our information, so I said we wanted to know where the function was increasing or decreasing, so I could say then that this function is increasing on this interval from -infinity to -2 and on the interval from 0 to infinity, based upon the sign of the first derivative. We know that the function is decreasing here between -2 and 0, so decreasing on that interval from -2 to 0. And then the local max and local mins, depending upon that change in sign, right, of the first derivative. So if we go from positive to negative, like we do at -2, we're going from increasing to decreasing. That would mean we have a local max at x equals -2. Specifically, it would be the point -2, approximately 0.5413. But in terms of, what we were asked for, we just were asked to find those values for x. If I want to actually graph the function or sketch the graph, then maybe we could find the y-coordinate if you want to use that to do a more accurate sketch of your graph. Then at 0, we're changing from negative to positive, which means we're changing from decreasing to increasing. So that would give me a local min at the point where x equals 0, which is the point 0, 0. Now again, the ordered pair is coming from the function, right? The ordered pair, anytime you're looking for a point on the graph of the function, make sure you're plugging it back into the function and not the derivative, because if you plug it into the derivative, you're going to get 0. That's how we found them, remember? So be careful. Like I said, you just need to be organized. Make sure you're plugging things in correctly. I went ahead and did a rough sketch of the graph just to show, it kind of jives with it. And then keep that in mind, too. I mean, when you're trying to find this information, you can always look at the graph of your function to see the behavior, Now, you're still going to have to go through all the calculus, all the math to prove the information or verify it. But you can always pull the graph up on your calculator, and if you get a decent picture of the graph, you can very easily see what the behavior of that function is. So you can kind of use that to double check your work to make sure that what you got, is reasonable, right? Or it kind of makes sense based upon what you see on the graph. So don't forget that. Use that to your advantage. You still have to do all the math, but at least you can verify whether what you've done is correct or not. Here's another one. Let's let f of x be the function x to the 2/3. Right? So just kind of giving you some different looks with different functions here. So again, same question. Where is the function increasing or decreasing? Where does it have any local extrema? So this would be a case, because if you look at f prime, right, so we say start by finding the critical numbers. Again, a nice little power function. So 2/3 x to the -1/3. And then I just went ahead and rewrote it, dropped the x to the -1/3 to the denominator. I went ahead and put it back in radical form as well. This is our derivative. We are going to have to evaluate that thing to determine the behavior of our function. But in this case, we do have critical value at x equals 0, because that would be a value for x where the function is undefined, our derivative. So remember, that's our critical numbers. Now, if you set that equal to 0, that's never going to equal 0. The numerator of that fraction is 2. I mean, the only way you get a fraction equal to 0 is if you have a variable up there. The fact that the numerator is a constant means that that function would never equal 0. It's not possible. But we do know that it's undefined for x equals 0, so that is our critical number. So here's our derivative. Here's my little test strip. Go ahead and label that. That is f prime. And then I took sample points. In this case, since my only critical number was 0, I just chose -1 and +1 as my sample points. So if I plug in -1, and again, I don't care about the number. All I care about is whether it's positive or negative. All right, so, if you plug that into your calculator and you get a funky decimal number, that's fine. I don't care. All I care about is whether that number is positive or negative, because that's the information I'm interested in. But if you plug in -1, you do get a negative value. So we know that the function is decreasing on that interval. If I plug 1 into that derivative, I will get a positive value. So now I know that the function is increasing on that interval. So we're decreasing on this interval from -infinity to 0 here. And then we're increasing on the interval from 0 to infinity. Okay? And because of the fact that we are changing from negative to positive at 0 with respect to our first derivative, so we're going from decreasing to increasing, we know then that there is a local minimum at the point where x equals 0. Which again, if you plug that back into the function, gives you 0, so it's at the origin. And if you were to graph that function, there's a little sketch of the graph of that function and what it looks like. So notice that we found that critical number. That was where our derivative was undefined. So notice on the graph of that function, you have a corner there, right? That's one of those corner locations, which we said is where a function would not be differentiable, okay? But again, using the graph to kind of verify my information. But again, what am I interested in? Where is it increasing? Where is it decreasing? Where is the local extremum? Now, second derivative. I've said that we're going to bring this into it. What does the second derivative tell us about the graph of our function? Right? What does f double prime tell us? All right, let's see if we can do this a little bit. As always, there's a fancy definition down here for this. We'll talk about this in a second. How about a more general observation first of all? All right. So remember, what does the second derivative tell us? Right? The first derivative gives you the rate of change of the function. Right? That was our increasing or decreasing. The second derivative, remember, is going to give you the rate of change of the first derivative. Right? Each successive derivative is the rate of change of the previous derivative, whatever that measures. So the first derivative is whether the function values are increasing or decreasing. The second derivative is whether the first derivative is increasing or decreasing. Now remember, what is the first derivative? That's the slope. So the second derivative tells you whether the slope of your curve is increasing or decreasing. Okay? So let me try this. I'm going to use maybe some different colors here. What about the yellow? So if you look at the first part of this graph that I have on the right, for this part of the graph, what's happening to the values of the slope of the curve, right? It's positive slope because it's increasing. But notice that the values for the slope itself are getting smaller, right? Because the graph is getting less steep as you travel along that portion of the graph. So the values of the slope are decreasing, which means, what does that mean about the second derivative then? If it's a decreasing first derivative, that would mean that the second derivative was negative. Isn't that how it works? If the first derivative is positive, the function's increasing. If it's negative, the function's decreasing. So if the second derivative is positive, the slope would be increasing. If the second derivative is negative, the slope would be decreasing. So in that case, the slope values are decreasing. It's getting less steep. So that would tell me that over that little portion that I've traced in yellow, the second derivative would be negative. Now notice at that turning point, we still have a decreasing slope value, because now the slope value is negative, but it's getting more and more negative, right? It's getting steeper negative, but so it's getting smaller, right? So the slope values continue to decrease. So my second derivative is still negative there. So in the portion that I have traced out in yellow, that's a negative second derivative. Now, what happens right there at that point where I stopped? Notice that at some point right here, the slope values start to increase. Right? They're still negative, but they're getting less negative. It's less steep. So the slope values are increasing. Well, if the slope values are increasing, then what does that mean? That means that the second derivative would be positive, right? And notice as we trace out the rest of this curve, the slope values continue to get larger, right? They go from negative to positive, and then the graph gets steeper, and over that blue part of the graph, the slope is increasing. So the second derivative would be positive. The behavior that we're describing here, what this second derivative tells me, we call this concavity. Wherever your second derivative is negative, we call that concave down. That was the yellow part of our graph. Wherever the second derivative is positive, the blue part, we call that concave up. But that kind of, it gives you an idea of what the heck you're actually measuring when you talk about concavity. Now, ultimately, of course, all I care about is you know how to find it, describe it. But it's a little, it takes a little more understanding because you're talking about now the second derivative and how that relates to the actual graph of the function itself. Okay? All right, so we're going to get back to that in a second. Here's the formal definition, though, of concavity. Let me change that back. Our definition says that if the graph of a function f lies above all of its tangents on an interval, then f is said to be concave upward or concave up on that interval. So on that blue part of the graph that I said was concave up, notice that if you drew a tan line to any part of this graph, at any point on that portion of the graph, the tan line is always going to be, I keep drawing in the wrong place, the tan line is always going to be below the graph. Or in other words, the graph is above all of its tan lines. Okay? We say that's a concave upward graph, or that the graph is concave up on that interval. And then vice versa. If the graph of f lies below all of its tangents on that interval I, then f is said to be concave down. So if the graph is below the tangents, then the tangents are above the graph. So that yellow part of the graph, notice if you draw again tan lines to any point on that graph, the graph is always going to be below the tan lines. That's the formal definition of concavity, all right? Whether the graph lies above or below the tan lines. It's not a very workable definition. I mean, it makes perfect sense when you look at it. But we have a more useful kind of way to determine, or an easier way to determine whether the graph is concave up or concave down. The graph on the left would be an example of a graph that's concave down. The graph on the right is a graph that's concave up. Here's an easy way to tell if you're not sure. Looking at the graph, take your hand and put it palm down. Doesn't matter which hand, use your right hand, use your left hand if you're left-handed. I'm using my right hand because I'm going to trace the graph from left to right. Okay? So I put my right hand palm down. Now, with your fingers, trace the graph. So just start tracing the graph with your fingers. And notice that your fingers are going to start curling down as you trace along that graph. Concave down. Now notice what happens on the right side. Again, if you put your right hand palm down, now take the tips of your fingers and start tracing the graph. What happens to your fingers? They're going to have to start curving up, right? And they can't curve up, but your hand wants to curve up. So your fingers are going to want to start bending backward. Your hand has to curve up. That's concave up. So it's a very easy way to tell just by tracing the graph with your hand. So put your hand palm down and then trace the curve with your fingers. And if your fingers want to curl down, the graph is concave down. As soon as your fingers want to start bending back up, you're concave up. Okay? So we're going to call this the concavity test. Now remember when we did the test for the increasing and decreasing, we called that the first derivative test. I'm not calling this the second derivative test. There is a second derivative test. but it actually is used to measure increasing and decreasing. So don't call this the second derivative test. You're going to confuse yourself if you do. So I call this the concavity test, or test for concavity. All right, so just like we said, if the second derivative is positive for all x in an interval, then the graph is said to be concave upward or concave up on that interval. If the second derivative is negative for all values of x in our interval, then the graph is said to be concave downward or concave down in that interval. A point P on a curve y equal f of x is called an inflection point of that function if f is continuous there. There's our good old continuity as always. And the curve changes from concave up to concave down, or concave down to concave up. So remember when we were doing increasing and decreasing, how did we find or start to determine that information? We took our first derivative, we set it equal to 0 to find what? To find the critical numbers. Right? Wherever the derivative was 0 or undefined, we found our critical numbers. And then we used those critical numbers to set up those subintervals on our test strip, and then we plugged in test values to determine the sign of the first derivative. Here, we're going to be looking for what is called inflection points. Where do I find inflection points? Where you have a change in concavity, which again, concavity is determined by the sign of the second derivative, positive for concave up, negative for concave down. So where do you think I'm going to start looking for inflection points? Where the second derivative is negative. Okay? So we don't call them critical numbers again because that'll confuse us with our first derivative. So I call them potential inflection points. Right? Now, it's not an inflection point unless you actually have a change in concavity. Okay? Otherwise, it's just a point where the second derivative is 0. All right, so same idea, just we do it with the second derivative, and the information that we're getting is different. So like I kept saying earlier, now that we brought the second derivative into it, you've just got to keep them straight. You know, which derivative am I using to get what information? Label everything clearly. Don't get them confused. So let's take, for example, in this case, I've got the function f of x equals x cubed minus 3x squared plus 5. And I'm simply asking you to find the inflection points. I will also mention the intervals of concavity as well. So for inflection points, for concavity, we need the second derivative. So we'll start with our first derivative, f prime, 3x squared minus 6x. Again, a nice little polynomial to start out with. And then we'll find our second derivative, 6x minus 6. And then we want to find those possible inflection points by setting that second derivative equal to 0. Okay. And then solve that equation, so 6x minus 6 equals 0, or x equals 1. And then we'll set up a test strip for the second derivative, just like we did the first derivative. And we're checking here for concavity. So notice I labeled this as our second derivative, f double prime. That's a test strip for that function. And then we'll plug in sample points just like we did with our first derivative. So I didn't write it out. Let me go ahead and do that. So let's say, for example, I plug in f double prime at 0. All right. So again, you're plugging those values into your second derivative, into this guy. And if you plug in 0, you will get negative 6. So f double prime of 0 is negative. It's less than 0. And then we'll pick a number on the right side of 1 in that other interval. Let's say 2. Now again, I'm plugging this into f double prime. So, you know, try to be consistent. Make sure you label everything clearly. So if you have to go back and find any mistakes, or when I'm looking at your work, it's easy to follow. So I'm plugging in 2 into that second derivative. That would give me 2 times 6, 12, minus 6 is a positive 6. So it is a positive value. And so then on that interval from negative infinity to 1, we would say that our function is concave down because the second derivative is negative there. On the interval from 1 to infinity, the function is concave up because Our second derivative is positive, and since we have a change in concavity at 1, then at the point where x equals 1, we have an inflection point. Now, this is an inflection point on the graph of our function, so it is customary to go ahead and find the ordered pair. Okay, so it's usually not sufficient here just to say, oh, there's an inflection point at x equals 1. That's true, but we want to go ahead and give the actual point because it is called a point. Okay, it has a y coordinate. So I have an inflection point at 1, 3. And again, there's a rough sketch of the graph of that function. So notice as we go on the left side of 1, there's those fingers curling down. We're concave down. And then at 1, we change to concave up. Excuse me. Now, there is a second derivative test. The one I just showed you, I called the test for concavity, or the concavity test. I didn't call it the second derivative test. I'm going to show you the second derivative test. It's an optional test. Second derivative test is also used to determine where your function is increasing or decreasing, or where you have, more specifically, a local max or a local min. But we have the first derivative that we can use to determine that. So, and I don't think that's a difficult process, but, if you want to use second derivative test, you're more than welcome to use it. I just typically don't find the need for it because the first derivative can be used to do it anyway. But, it's either or, whatever you prefer. But here's how this works. And so it kind of puts into conjunction what we just talked about with concavity, to where if we find, say, f double prime is continuous, we always want continuity. That seems to be a part of every definition and theorem that we talk about. So suppose f double prime is continuous near C. So our second derivative. If f prime of C equals 0, which means that C is a critical number, right? So if f prime of C equals 0, that's a critical number. And the second derivative is positive. Well, what does the second derivative positive mean? It means that the graph is concave up. Well, if we know that we have a critical value or a critical number at that C value and we're concave up, then what has to be true? It means the graph has to be doing this. It means that there would have to be a local minimum at that C value because of the concavity and the fact that the derivative is 0 there. And then vice versa. Right, so we have a local min at C if that's true. And vice versa. If, again, we have a critical number at C, so f prime of C is 0, and the second derivative is negative, so that means we're concave down at C, then that would mean we would have a local max, because we're concave down, and we have a critical number there, the horizontal tangent. So we have a local max. Okay. So the second derivative test, it's used for identifying local maxes and local mins. But like I said, we typically don't bother using it just because the first derivative test works well enough to do that anyway. So, if we have to find where it's increasing and decreasing, I can tell you where there's a max or min without having to use the second derivative to do that. Okay. But, they will mention it in the homework, and they'll say, use the second derivative test to determine local max and min. I don't care if you use second derivative or not, because I never use it. Now, here's kind of a little drawback of this test. So notice if f prime of C equals 0 and f double prime also equals 0, right? So everything was based upon whether we were positive or negative with our second derivative. Well, if both of those are 0, then guess what? It doesn't tell me anything. Or if f double prime doesn't exist, then this test doesn't tell me anything. There could be a max, could be a min, or could be nothing. So then I have to fall back on another method, which is using the first derivative, right? So, yeah. Anyway, let me give you an example with that just to see it. But like I said, again, I'm not typically going to bother using it at this point anyway. Maybe later when we can do some application stuff, but I'm just going to go ahead and leave that as an optional process for you at this point. So this is the one that we did earlier. We did the function f of x equals x squared e to the x, and we found the maximums and minimums using the first derivative, and we did the increasing and decreasing. and we found that there was a minimum at 0 and a maximum at x equals 2. And that's what we found using the first derivative. So here's the same thing using the second derivative. So we still have to find the critical numbers. So we still have to find f prime. We still have to set f prime equal to 0. And again, we're going to get the same critical numbers we got the first time, 0 and negative 2. But then, second derivative test says, okay, take the second derivative. Now, depending upon our function, how much work is involved there, but this is another product rule. So that's first d second plus second d first, or again, I just factored out the e to the x and combined the remaining terms. There's our second derivative. Now again, remember, like we said before, with the e to the x, that's always positive. I don't care about that. What I do care about is this other factor and whether it's positive or negative to give me the sign of the second derivative. And again, we plug in those c values, right? Because we said once you find the critical numbers, that's what you want to plug into the second derivative to determine if you're concave up or concave down there, to tell me if I have a max or a min. So if you do plug 0 into the second derivative, you will get a positive value. So that means that the graph is concave up there. Now again, this is also kind of backwards from what we saw with the first derivative. Since we're concave up, a positive second derivative actually means that I have a minimum at that location, because remember we said the graph is doing this. And then if you plug in negative 2, f prime of negative 2, you will get a negative value there, which means we're concave down. And again, that would then mean that there is a local max because the graph is doing that. Okay. But like I said, I find it's probably more confusing than anything. I would just stick with the first derivative when you're doing increasing and decreases and maxes and mins. Now, once we start asking for concavity and inflection points, then you definitely have to bring in the second derivative. Right? That's the information you get from that. All right, so here's one final example. So here's everything involved. This is a typical test question right here. Here's a function f of x. Find the intervals where f is increasing or decreasing. Locate any local maxes or mins. Identify the intervals of concavity, any inflection points. Now, I may or may not ask you to graph it. I'm going to do a sketching of the graph for this one just to show you how we can do that. Because like we said, ultimately that's what this is all about. We can use the derivative, and in this case also the second derivative, to give us information on what the graph of our function looks like. Okay, so I'm going to sketch this one out using that information, but definitely parts A, B, and C is what you would see on a test. So increasing and decreasing, I'll take my first derivative, so for f prime, and again this is a nice little polynomial. So here's f prime, 4x cubed plus 24x squared. We set that equal to 0 to find our critical numbers. Now again, remember I'm looking for increasing, decreasing, maxes and mins here. So first derivative equal to 0 to get our critical numbers. I went ahead and factored it. I could pull out a 4x squared times x plus 6. Set each of those equal to 0, and I've got x equal to 0 and x equal to negative 6. So there are our critical numbers. There's my test strip for f prime. And then we just plug in our sample points. Whatever you want, something in the interval to the left of negative 6, I plugged in negative 7. You end up with a negative value. Now again, I'm plugging this into f prime. And then between negative 6 and 0, I just chose negative 1, any number in that interval. And that one will give you a positive value. And notice this one, because like I said earlier, don't presume that they're always going to alternate positive, negative, positive, negative. Notice that this one, when you plug in something from this interval, I plugged in 1, you also get a positive value. So you've got two intervals next to each other that are both positive first derivatives, which means that it's increasing and then it's increasing again, right? So that's it. Make sure you check. Don't fall into a trap. All right, so then in terms of increasing and decreasing, I'm just going from left to right. We have that our function is decreasing on the interval from negative infinity to negative 6. That's where we have that negative first derivative. And then our function is increasing on the interval from negative 6 to 0, and also on the interval from 0 to infinity. Now, technically, I would prefer to put those as separate intervals, but if you list those together, I'm okay with that. Because it's increasing, and then right at 0, remember, we get a horizontal tangent there. So it's kind of, think of the graph as increasing, then it flattens out right at that point, but then it starts increasing again. So since they're adjacent intervals, if you want to go ahead and put them together, that's fine, or list them separately to be on the safe side, either way. So then in terms of maximums and minimums, right, so where do we have a change in the sign of our first derivative increasing to decreasing, or vice versa? And that's occurring at negative 6, where our derivative is changing, right, from negative to positive. So we are changing from decreasing to increasing, which means that there then is a local minimum at that point where x equals negative 6. Now I went ahead and plugged negative 6 into my function to get the point on the graph, because I am going to sketch the graph. So I went ahead and plugged it into the function itself. And if you plug negative 6 back into f, you will get negative 232. So there is a local min there. Now notice there is no local max in this case. All right, so there's no guarantee you ever have either one or both. There is no place where I went from increasing to decreasing. So there is no local max for this particular function. All right, so that's our first derivative, gave us the increasing, decreasing, and local extrema. Then we'll bring in our second derivative to get our concavity. So second derivative, f double prime, and again, this is just power rule for this function. There's our second derivative. And again, we're setting it equal to 0 to find potential inflection points. All right, when we did the first derivative equal to 0, that's finding your critical numbers, which could possibly be locations of maxes and mins. For the second derivative, setting that equal to 0, I'm looking for potential inflection points. And then we have to check the intervals. So there's a factored second derivative, 12x, x plus 4. So again, I get x equals 0, and then x equals negative 4. So those would be the locations of possible inflection points. So then there's our test strip for the second derivative. And then we'll take our sample points from each subinterval. So I went in and plugged in to the left of negative 4, I just plugged in negative 5. Now again, this is getting plugged into our second derivative. We're checking for concavity here. So if you plug negative 5 into that second derivative, you will get a positive value. Your function, your graph is concave up there. Between negative 4 and 0, I just chose negative 1. Plug in negative 1, you will get a negative second derivative, so we'll be concave down there. And then to the right of 0, I plugged in 1 into my second derivative. And again, you will get a positive value, which means we're concave up there. So there's our intervals of concavity. We're concave up on this interval from negative infinity to negative 4. We're also concave up here from 0 to infinity. And then we're concave down in between from negative 4 to 0. So there are our intervals of concavity. So we do have two inflection points here. We do have a change in concavity from positive to negative at negative 4. So there is an inflection point at negative 4. And again, I went ahead and plugged that into my function because I said I always want the point here anyway. But I am going to plot this so when I sketch the graph, we have the point. So I plug negative 4 into my function, and I've got an inflection point at negative 4, negative 56. Specifically, we know we're changing from concave up to concave down there. We also have an inflection point at 0 because we are changing from concave down to concave up. And if you plug 0 back into the original function, you will get 200. So here's the information that I know. Back from this first part, we found that the function was decreasing on the interval from negative infinity to negative 6. and then it was increasing from -6 to 0, and then again from 0 to infinity. So when I sketch the graph, and I've told y'all before with these, just start from the left and work your way to the right. Go from left to right on your graph. Find the important points on your graph. So, where does stuff happen? Well, we know we're changing, or we have critical numbers at -6 and at 0. So I went ahead and found the ordered pairs. I've got -6, -232, so I can plot that as a point on my graph. We know even more about that point. We know that there's a local min there because we're changing from decreasing to increasing. So I'm going to plot that as a point on my graph. And then the first thing I'll do is, okay, well, what's happening on the left side of that point? Am I increasing or am I decreasing? Am I concave up or am I concave down? Okay. Then after we pass -6, the next point of interest is -4, right? Because that's where we changed our concavity. So my next important point is -4. So again, we found that to be, or have ordered pair -4, -56. So I plot that as a point. So then what I do is from -6 to -4, what's happening? Am I increasing or decreasing? Am I concave up or concave down? Right? So in other words, what's changing at each of these points that we're finding on our graph? And we change accordingly until we hit the next point of interest, which would then be at 0, which was the other point that we found. 0, 200, we're changing concavity again. All right. So just again, to give you an idea of how that would work. Right. So if I look at this graph, we said on the interval, I plotted that point -6 to -6, -236. On the interval from 0 to -6, we know that we're decreasing. We also know that we're concave up, because we're concave up all the way to -4. So I'm just tracing out a graph that would be decreasing and concave up. Once I hit -6, though, what changes, we went from decreasing to increasing, but I still have to be concave up. Now, from that point forward, remember from -6 on forward, we're increasing. From -6 to 0 and then 0 to infinity. But what did change was at -4, we changed concavity. So you kind of have to do that little wiggle thing, right? So you're tracing your fingers and they're bending up, and then at -4 you start bending them down. Because at -4 we're now concave down, but we're still increasing, right? But then what changed at that point? We changed from concave down to concave up again. So, but again, I'm still increasing. Remember, we're increasing all the way to infinity. But at 0, we change from concave down to concave up. So, it takes a little practice. Like I said, I probably won't ask you to sketch a graph on a test, but, definitely you'll have to find all the information that I just found. But that's how you could use that, and you could do a rough sketch and give you an idea of what the graph looks like without necessarily having to graph it on the calculator, do all the window changes and all that, trying to get a picture of the graph. You can do a really quick sketch this way if you have that information. But anyway, so that's using the derivatives, first and second derivative, to give you a sketch of the graph of a function, behavior of a function. And that is it for